Okay, so carrying on with the topic of integration, there's quite a bit to it. This time we're going to be looking specifically at making use of trigonometric identities um, in order to do our integration, and that's a bit of a vague sort of category of integral problems. So I think very much it's the case where you just need to see a few different examples of the kinds of questions you might get. So I'm mainly just going to go through a few examples, I think 3, and then you can try a few yourself. But the key thing here is that you come prepared with a knowledge of several trigonometric identities, so that way you can convert, from things involving sine and cos, or double angle, or compound, things like this. You can convert them to something else, which you can then integrate. So just to start us off, because perhaps you may have not done it for a while, see if you can remind yourself, how do I write cos 4x as I suppose a polynomial, but it's a function, it's a polynomial function containing only cos x. So no cos 2x's, no cos 3x. You can have cos x squared, but as long as the x is an x and it's not a multiple of x. See how you do. Can you find out what that would be? So to do this, we're going to make use of the following property, that cos of 2, let's use theta so we don't get confused, is equal to 1 minus, well, there's multiple versions, isn't there? There's 1 minus 2 sine squared theta, or it's 2 cos squared theta minus 1. And there's also a third version, which we're not going to use. So we're going to use that version, and we'll proceed as follows. We're going to say cos 4x equals cos of 2 times 2x. So now it's converted to a double angle. And then cos of 2 times something is equal to 2 cos squared of that something, which is 2x minus 1. And then we're going to repeat ourselves a bit. So now we've got 2 times cos 2x, which is squared, effectively, minus 1. So let's replace that again with 1 minus 2, oh sorry, 2 cos squared minus 1. So now we've got this. And we're slowly getting there. So we've got 2 times squaring everything on the inside, minus 2 times the product. Let me just check I haven't rushed this. And then we'll multiply that out. So we get 8 cos to the 4x plus 2 plus 8 cos squared x minus 1. But then we can actually, that plus 2 and the minus 1, we can just replace that with a single plus 1. That looks, oh, I thought I made a mistake. Yeah, here. That should be negative. Well done if you spotted it before I said it. That should be negative. So as a consequence, that should be negative. Okay, and that's it. So in theory, you could do that for any powers of 2, cos 8x, cos 16x. It will just start to look a bit horrendous. So this is an example of one way in which we might perhaps make a function more integrable or more possible to integrate. For instance, if I said, now integrate that thing, if I said integrate this, what you'd actually do is you'd convert it into that, you'd reverse the process, and you can integrate that. You can integrate cos 4x. It's just a quarter sine 4x. So actually the integral of that function is just quarter sine 4x. Though it may not be that immediately obvious, because you have to convert from one trigonometric expression to another. So that's what this chapter is all about. It's use trigonometric identities to get from a function you can't integrate to one you can. In this case, we kind of did the reverse. We went from a function we can integrate to one we can't. But it's good practice in any case to remember the equivalence between these two. So let's look at our examples. So first of these, it looks simple. I think it's worth giving it a go if you're, before you see me do it. Don't think it's sec x, by the way. That's not the answer. It's the integral of sec squared, which is tan. But what's the integral of tan squared? So the way we're going to do this is we're going to make use of, and I'm going to write it shorthand here, sine squared plus cos squared equals 1. Divide everything by cos, and I get tan squared plus 1 equals sec squared. So in other words, tan squared equals sec squared minus 1. So this is the same as the following. It's the same as sec squared x minus 1 integrated. So now we can integrate it, right? Because we know the integral of sec squared. The integral of sec squared is tan. And the integral of minus 1 is just x plus c. That's it. We did it. Not too bad, right? So you've got to get used to using those trigonometric identities. And then on top of that, you have some kind of a sense in your head of what things do I know how to integrate and what things don't I know how to integrate. I can't integrate tan squared. I can integrate sec squared. So is there a relationship between tan squared and sec squared? Of course there is. It's this one. So we're kind of thinking multi-level here. Let's have a go at the next example. Okay, so we've got a definite integral here. No worries. The main sort of technique is going to be in the actual integration. So, okay, again we're thinking, right, sine squared, I don't know how to integrate that because of the square. What can I convert it to which I can integrate? Well, I can integrate things like sine and cos. I can integrate things like sine 2x and cos 2x, or sine 3x and cos 3x. So can I convert sine squared into something that does not have the power? And yes, we can. So there's the way we're going to do this is we're going to consider this function, right, the one we just spoke about, cos 2 theta equals 1 minus 2 sine squared theta, and we're going to rearrange it, and we're going to make sine squared theta the subject. So if I rearrange that, I get sine squared theta equals, and I'm doing it in my head a little bit, 1 minus cos 2 theta divided by 2. Okay, so rearrange the top, you get the bottom. So that means that this thing is the integral of, I'm just going to call those A and B for now, 1 minus cos 2 theta divided by 2, oh sorry, not theta, we're on x, my mistake, 1 minus cos 2x with respect to x, and the divide by 2, to make it easier on ourselves, let's put it on the outside, because it's just a constant multiplier. So that we can now easily integrate. The integral of 1 is x. The integral of minus cos 2x is minus a half sine 2x. Right? And then we've got these limits a and b, which are actually pi over 12 and pi over 8. Okay. The rest of it now is something that we should really be familiar with. I don't know if it's worth necessarily finishing that off, but I think I'll leave it as an exercise to you. Classic, leave exercise to read it. So if that's something you think, I know how to do that, I'm familiar with using my surds, I know how to find sine 2x if x is one of these values, and you can skip. If you're not sure, see if you can finish that off. You know what you're aiming for. You're aiming to get that number. Okay. I'll just double check so I don't mislead you. That is in fact the correct integral. Yeah, that has been done correctly. In the textbook, they haven't taken the half out. I think it's a good idea to take the half out because you're just working with one less fraction, effectively. So if you want to, see if you can finish that off. See if you do in fact get this. So you can pause now if you're going to try that. Okay, so a two-parter on our final example, and this is where the whole thing about remembering the formulas rather than relying on the formula book so that you can spot patterns. So what is the pattern I can spot here? It's that I've got sine of something times cos of something, right? They're both 3x. And sine A cos A, that almost looks like 2 sine A cos A, right? And then that's the trick here. So we remember that sine of 2A is equal to 2 sine A cos A. So if I multiply both sides by a half, I get a half sine 2A equals this, sine A cos A. I can integrate sine 2A, so that means I can now integrate sine A cos A. So let's rewrite this. This is the integral of a half sine of what now? Well, the A is 3x, so that's going to be half of sine of 2 times 3x. So let's just write it in full actually. So it's 2 times 3x. And to make that a bit simpler, I'm again going to take the half on the outside out. And this just becomes sine of 6x dx. This is then a half of, and then we do the integration. So we should get minus a sixth cos 6x equals minus a 12th cos 6x. And indeed that is the answer, but with a plus c, because it is an indefinite integral. Cool, okay, and then the last one, sec x plus tan x all squared. So for this one, there's no obvious way to simplify sec x tan x, but what we could do is, if you think to yourself, okay, if I square that, I'm going to end up with sec squared, tan squared, and sec tan. And I know how to integrate sec squared, and I know how to integrate tan squared. In fact, that was the very first example we did. And we do actually know how to integrate sec tan as well, because that's one of the standard results we had. So let's try multiplying it out. This is the integral of sec squared x plus tan squared x plus sec x tan x. And then we can now split this up into its separate parts, right? So we've got the integral of sec squared x tan squared x and sec tan. And the integral of sec squared is just going to be, oh hang on, have I missed something here? No, I don't think so. So integral of sec squared is tan x. The integral of tan squared, you wouldn't know this off by heart, but based off what we did earlier, we know that it's tan x minus x. Okay, so go back to the previous example if you've forgotten why that's the case, and you would in fact work that out in a method that's similar to the previous example. Convert it to 1 plus sec squared, or sec squared minus 1, and then sec tan, which I find the easiest one to remember. Integral of sec tan is the sec tan function, so that's just sec, and then we've got our plus c. So remember that third one, that's a standard one. To prove that, you actually just consider sec as 1 over cos, and you do the quotient rule, and you do find the derivative, you end up with sec tan. So simplifying that, we get 2 tan x. Oh, sorry, hang on, this is not quite right, is it? Sec x tan x. That should be Silly me, there's a 2 here, isn't there? I've rushed. Never rush like I rush. So that's 2, and then we get 2 there. Yeah. Yeah, so I forgot to double it when I did the product. Okay, and then we got 2 sec x and minus x plus c. You could rewrite it this way. Don't know if that's necessarily, that's not really necessary, but to be honest, I always think it's quite a nice, and it's a bit of a beautiful result if you can have an integral which contains within itself sort of commonality between the original function. So you've got this sec x plus tan x going on here, and you have it here as well. Sometimes you might be able to reveal interesting properties about the functions involved, but we won't go any further with that. The point being is you should be able to integrate this, and this is how you're going to do it. Cool. All right, so time to try some questions yourselves. Okay, so it's just a single slide. All the questions are there, but they may take a little bit of time. So don't rush. Just try and complete them if you can. For part 4, if you're struggling on, say, the first 2, make sure you get help with that, and then see if you can move on to the later ones, just because there are quite a few parts there. However, I do think they are sufficiently different that it's worth trying all 4 of them if you're making good progress. So give those a go, pause the video and see how you do. Ask me for help if you need it.